All right, let's do a little pre-talk test, shall we? Those of you who have watched me before have an idea of what these are. So I'm just gonna test that audio is working fine. How is volume for everyone? That's both YouTube and Twitch. How does my voice sound? Does it sound okay? Are there any weird echoes, anything like that? Good to me from Twitch. What about YouTube? Perfect. Well, I doubt that very much, but good. I'll settle for good. And Twitch and YouTube, can you see each other's chat messages? Great. YouTube and Twitch both have good volume. Twitch can see YouTube, and YouTube, as usual, is has a delayed signal compared to Twitch. So in like 5 seconds, I'll get a long batch of messages from YouTube. Fantastic. There we go. A lot of familiar names. That's exciting. All right, I guess it's time to test video. We're getting close enough to do that. So if I do this, then in theory, now you should see me. Is that accurate? Can Twitch see me? Can YouTube see me? Twitch goes first. Yeah. YouTube goes second. I think the delay is quite significant. It's like almost a 10-second delay from when Twitch responds to when YouTube responds. Sometimes even more, actually. Yeah, it's 20 seconds. The quality is really good. Okay, that's what I want to hear. Because Twitch rules, that's right. In theory, though, the quality should be about the same, and the delay probably won't matter much for a talk, although it might matter for the questions later, but it should be fine. Okay, so we've got video, we've got audio. Thank you. To everyone who says good luck, thank you. I appreciate that. We're more chill over here at YouTube. That's funny. Last time I had some people giving feedback on the talk, and one of them said that the background was distracting because I had my red chair behind me and some stuff on the shelf. So I've tidied it up a little bit. So in theory, we should be good to go. Got my lapel mic and my other mic. So hopefully it should turn into a good recording. All right. I guess it's 2 p.m. So I'm still waiting for people to file in. I think we're gonna do this on MIT time. And so even though start time is set to be, well, 2 p.m. my time, 9 p.m. UTC, we'll probably start like 5 minutes past the hour, and just give a little bit of, I'll just give a little bit of sort of setup before I actually get into the talk itself. I'll make sure to warn you before I start. The singular plant. Well, there's also a plant hiding, like right here. It's a sneaky plant. Also, this one is fake, but that one is real, and larger, but it's hidden. It doesn't get to be in the video. It's snake plant. All right, so let me do the sort of spiel before we start. For those of you who are maybe not familiar with what I'm doing here and why, I've ruined the illusion, I'm sorry. So I'm here to give essentially my doctoral dissertation talk. And specifically, this talk is essentially a presentation of the culmination of the work that I've done over the course of my PhD at MIT for the past 6 or so years. And this is not my actual thesis defense. There are two reasons for that. First of all, the defense itself, what's the thing in the bottom right corner? Oh, it's just a vent. First of all, the actual defense is happening tomorrow, not today, but it's happening over Zoom. And so that means that I can't just invite everyone, post like a public Zoom link, because it would be a disaster. And so instead what I'm doing is I'm doing the same talk that I'm doing tomorrow today, so that you, the beautiful people of the internet, can actually sort of see it and experience it. And hopefully you'll find it interesting. The second is that the doctoral defense is not really the talk. The talk is intended for a wider audience and is generally considered like tradition, but not a requirement. Not always, this varies by institution, but at least at MIT, everyone does it, but you're not required to. Like your committee is reading your thesis, and that's the thing that you're defending. And that usually happens after the talk, which is going to be tomorrow. Someone asked, am I able to legally stream this? Yes, this is my own presentation and my own work, and there's nothing that prevents me from presenting this. And so what I'm going to do for this presentation is basically, I'm going to give the same talk as I'll be giving at MIT tomorrow, and I'll be giving it as if it were the real deal. And so I will do the whole thing start to finish. I will not take questions until the end. I'm going to record this whole thing, so anyone who's interested, I'll be posting the final thing online afterwards, and I'll tweet out the link and such. And are there any other details? Yeah, this also means that for those of you who are participating in the chat, I will not be interacting with chat during the talk. Instead, I will just be giving the talk as if you were sitting in an audience and everyone being quiet, although you have the luxury of being able to whisper among yourselves, but I'll basically be ignoring that until I get to the end, and then I'm happy to take questions and stuff and try to answer that at the end. All right, we're approaching 5 minutes past the hour, so in like a minute or so, I'll start. Let me just finish, get set up. Great. This is my defense talk, yeah. Well, defense talk is a bit of a misnomer because it's my doctoral dissertation talk, but the defense is not a talk. The defense happens after the talk usually, and the defense is about the dissertation you hand in. In general, you can think of this as, it sort of makes sense, right? The talk cannot possibly capture everything that's in the thesis, so you're not really evaluated on the talk, except like you're evaluated by the public, so to speak. But the actual sort of, will my committee sign my thesis is going to happen tomorrow after the talk. All right, 2:05, I guess it's time to begin. So in theory now you should see my slides. Just check that is actually the case, otherwise this will end up having been a giant waste of time for everyone. So just a quick check that you can see the slides. It should say partial state and dataflow-based materialized views. And in theory, there should be an image of me in like the bottom right corner. Fantastic. We can. Okay, so Twitch can, so I'm going to assume that YouTube can as well. All right, let's get started. Let me just start recording here. Record there. All right. Hello everyone, my name is John and welcome to my doctoral dissertation presentation. This is going to be my attempt at summarizing the work that I've been doing over the course of my PhD at MIT for the past 6 or so years. The thesis I've been writing is on partial state and data flow-based materialized views, and hopefully by the end of this presentation you will actually understand what those words mean, and why that might be a useful thing to study for 6 years. This work is not entirely unsupervised. I have had a committee, in particular my advisor Robert Morris and Franz Koschweg, Sam Madden, and Malte Schwarzkopf are some of the people who are my committee, and they are some of the people who have sort of vetted this work and will be the final evaluators of my thesis. So I want to start the talk with, why are we here? Like, not in the existential sense, but in the sense of, why am I here? Why am I presenting you with this work? Why should you care? And we're here, or at least I'm here, to make databases better. That's my goal in all of this. In order to understand how we're going to do that, we need to look at how databases work today. So let's start with just a very straightforward, like databases 101. You have some tables. So in this case, let's imagine that we have the tables stories and votes, and they hold stories and votes. And then you want to query the data that's stored in those tables. And so what you do is you issue some queries to those tables. And the queries can look like all sorts of things. They might have aggregations, here indicated by a sum, or they might have joins, or all sorts of other operators. And all the work that's done by the reads, by the queries, is indicated here in orange. If you want to do a write, if you want to change the data that's in the tables, then you do an insert or an update or delete, and those changes go directly to the tables. And then when the data in the tables change, the queries then see the updated results. Now, in this talk, I'll be referring to queries as just being the reads that you can do. So things like selects. And even though inserts and updates and such are in SQL are queries, I'll not be referring to them as such. I'll be referring to them as writes or updates. Now, this is just generally how databases work, but there's a little bit of a problem with this model, even though it works well in many cases. And that is that there's a lot more work in orange than there is in blue. And what this means is that if you do reads, you have to do more work than if you do writes. And this is unfortunate because in many applications today, and in particular in web applications, there are just far more reads than writes. They're very read heavy. And so relatively speaking, there are many more reads, but the reads are more expensive. And that seems like an odd trade-off. And this problem sort of compounds when you look at applications that issue many queries over time. So you might see many queries that are identical or sometimes just similar, but a lot of the work is the same. And yet we're redoing it time after time after time, even if the table data hasn't changed all that much. And you might say, well, John, we have caches. Caches solve this problem. And in some sense, you're right. So caches are these storage systems that people place in front of their database. And they store the result from the queries that have been executed in the past. And the idea is that the query now just looks in the cache, and only if the result for the query they wish to execute is not in cache do they query the backend database. And it's true that now, in general, the work you have to do for a read is less. It turns out that this isn't a full solution, and we'll get into that over the course of the rest of this talk. There are some alternative approaches here, like denormalization, where you store and maintain derived values, like say a vote count in other tables, like in the stories table. But ultimately, these all have the same problem, which is that they're great, but caching is really hard to get right. Because what happens when the base table data changes is that the cache becomes out of date and it needs to somehow be refreshed. And so what this picture is trying to show is all the steps that are required that the application developers need to implement, right? If, say, a new vote comes in, it gets placed in the votes table, but now we also need to invalidate the cache somehow or update it in place so that later reads actually see that new data reflected in the data they get back. And then there's also this mechanism where if a query misses in cache, it has to go execute the query. But what if we happen to invalidate some entry that corresponds to a very popular story? Well, now, say 100,000 people want to read that story, so 100,000 application requests all execute the same query, they all miss in the cache, and they all go back to the database and sort of overwhelm it. And that would be very unfortunate. Even if we solve that problem, though, when the result comes back from the database, the result still has to be filled into the cache somehow. And then the question becomes, who does that? Because if you have these 100,000 requests, are all of them going to write to the cache? Because if so, that might be a problem too. And even here, if 100,000 clients all re-execute the same query, we're still redoing a lot of work. And this is particularly problematic if the data is changing somewhat frequently. We also have this other problem that over time, we're going to start to just accumulate a lot of data in the caches. And we only have so much memory. And so we need some mechanism to evict from that cache over time as data becomes unnecessary or stale. And then the question again becomes, who does that eviction? Ultimately, the observation I made in my thesis is it would be great if this was automated, if the application developers did not have to do this themselves. And to that end, what I wanted to explore was automatic database caching. And that is what my thesis implements and what we're going to be looking at for the rest of this talk. And in order to explore how we achieve automatic database caching, what we're going to do is we're going to go back to the title that I mentioned to you in the very beginning, partial state in dataflow-based materialized views. And what we're going to do is we're going to parse that title from right to left in order to understand what my thesis implements. So let's start with materialized views. And we're going to look at why materialized views are a useful abstraction in this context and what they even are. Materialized views were invented by the database community back in like the 1980s. And at the core of it, it's not that complicated. It really just means run the query and then remember the results over time. And this is sort of the same as for caching, right? That we just remember the result, and then when we next execute the query again, we can just read it from the materialized view, and the read will be fast. But here, just like in caching, the key question becomes, how do we maintain this materialized view as the underlying data changes? Ideally, we want this mechanism to not only be able to invalidate state that is no longer correct or accurate and has become stale, but we would like that process to be incremental so that we don't re-execute the query from scratch each time. Imagine, for example, that some story has 100 million votes, and then one more vote comes in. Well, if that one vote causes that story's count to be invalidated, then now the next query that comes along needs to count to 100,000,001, and that is potentially a really slow process. It would be better if the maintenance mechanism realized that one more vote just means +1 to this number, and we don't really need to re-execute all of the work. There's another question that arises in the maintenance of materialized views, which is, do we maintain the materialized view when the data changes, so sort of proactively, or do we just maintain it whenever reads come in, sort of reactively? And there are many designs for both systems. What we're going to be looking at here, and this brings us to the next word or the next set of words in the title, is we're going to be using data flow to maintain the materialization as the data changes. And data flow-based systems is sort of a systems architecture. And in fact, data flow has many definitions, both within and outside of computer science, and even within computer science, the definition varies a lot. Here in this talk, we're going to be considering data flow as having the data move to the compute. So you can think of this as, instead of code that fetches data from the tables, we're going to have the tables send data to various bits and pieces of compute so that they ultimately end up maintaining whatever state is downstream. You can think of this sort of as push-based computation. And the data changes are going to propagate through a graph of operators. And the operators here are relational operators like joins, aggregations, and filters, essentially any kind of operator that you would see in a SQL query. And the reason we're going to have this be a graph is we're going to have the edges of that graph represent data dependencies. So for example, a join would depend on, have an edge to, both or all of its input tables or input views. And then the messages that flow over those edges are going to be deltas. Now, deltas are essentially the same as rows. These are rows you would get back from any query you issue, but they also have a sign, which is either positive or negative. A positive sign is sort of an additional result. Think of it as, in the past, the query result set did not contain this row, but with this positive record, it means it now also contains this row. And conversely, if you get a negative sign, what a negative sign means is that an output row that was in the result is no longer present. It should be revoked. And in particular, for the purposes of this thesis, we're going to be looking at Noria, which is an eventually consistent materialized view system that is based on data flow. And this might be a little bit hard to grasp. So let's work through an actual example of a query that fits together. So here I show you a SQL query on the left and the data flow for that query on the right. And in particular, the data flow that Noria would end up using. So here you see we create a materialized view. We give it a name, story with VC, VC here for vote count. And the query is pretty straightforward. It joins stories and votes. And then every output row is going to be a story alongside the count of votes for that story. And if you sort of squint at this, you can see that pieces of this query are represented in the data flow. In particular, you see that the aggregation is pulling information from the fact that there's a count happening and what that count should be grouping over, right? So in this case, we want to group by the story ID, and by the join clause, we know that this is the same as the story ID clause in the votes table. Similarly, for the join, there's a join between stories and votes. And so Noria inserts a join operator that has a dependency on both the stories table and the vote count. Notice here that Noria has applied a little bit of query optimization. It's decided to do the aggregation first instead of the join first. And this is the kind of stuff that databases are generally allowed to do and helps increase performance. And now let's think about what happens if the application wants to read from this view shown at the bottom. Well, we have this view definition, but that contains the stories with vote counts for all stories. If the application queries for a particular story, it's going to execute a query over this view. So it's going to execute a query that looks perhaps something like this. Select all from story with VC, where the ID is, and then some parameter value. That might be 7 or 42 or whatever value the application supplies there. And that's essentially going to turn into a lookup into that materialized view that returns only the rows that match the parameter value that was given in. Think of this as sort of a key value lookup. And then what happens when the data in the tables change is that Noria is going to take the write, let's say it's a new vote for some story, and it's going to inject it into the data flow at the node that represents the table that the write was for. So if we insert a vote, we're going to push a new message into the data flow starting at the votes table node. And then it's going to stream down through the data flow, through all the operators. And as it flows through the operators are going to modify this update to represent whatever computation that they might perform. So for example, when the vote passes through the count operator, the count is going to convert a vote for, let's say, story 7 into deltas, one negative for the old count. So let's say here the old count was 42. So it's a negative row of 7, the story ID, and 42, the old count, and a positive, a replacement value of 7, the story ID, and 43, the updated count. You can think of this sort of as a statement of, it used to be that the count was 42, forget that, it is now 43. And then that delta is going to flow along down towards the join. The join then has to produce deltas that can be applied to the materialized view downstream. And that means that it has to include the columns from the stories table. And so when the delta flows into the join does lookups into the stories table and completes the additional columns that are specified by the query. In this case, stories.star, so all the columns of stories for the same story ID. And then ultimately, these deltas flow down into the materialized view and update that view in place so that subsequent reads from the materialized view now see an updated result. They now see story 7 have the vote count 43 rather than the vote count of 42. And now that we've been through materialized view and data flow, we're finally ready to tackle sort of the key contribution of this work, which is partial state. And partial state is pretty simple to explain why it's useful. And that is, we need to learn to forget. Chances are that most of the entries in the view that we just looked at are actually not accessed, right? Think of old and unpopular stories that are just sort of sitting around in the cache. Like someone read them a long time ago, but story 7 was published 10 years ago and no one is reading it anymore. If we're still keeping it in the materialized view, not only are we wasting memory, which is sort of a limited resource, an expensive one at that, but we're also wasting compute. And the reason for this is, imagine that there's still like occasionally a vote coming in for story 7 or something like that. Well, if we're updating story 7 but no one is reading it, that's also wasted cycles that we can instead use to compute something else that would be useful. And similarly for unpopular stories, if I post a tweet and like 2 people see it, but some celebrity posts a tweet and 1 million people see it, it's clearly more important to keep that celebrity's tweets in cache than it is to keep mine. We sort of need to evict things from the view so that the important things can fit there. Essentially, we need the ability to evict old entries and then only add new ones on demand. And to that end, the thesis makes three main contributions. It adds the notion of missing state in materialized views. So this is the ability to have some subset of the view just not be present. It adds upqueries as a mechanism to populate missing state using dataflow. And we'll talk about those later on in the presentation. And it has an implementation and evaluation of partial state in the dataflow system Noria. So the first thing we need to tackle is this notion that I explained earlier of the view and the query being separate. So the way that things sort of usually works is that you create this view and it doesn't have any parameter values in it. It just has all the result for all the stories. And then the application executes a query over that view. Unfortunately, this means that we don't really have enough information to make the view partial because we don't know how to determine the subsets of the view the application might care about. We don't know what key to use, what column to use as the basis for determining whether a given subset is missing or not. And so with partial state, what we're going to do is we're going to introduce the parameters into the definition of the view. So rather than have a separate view and query, we're just going to have a sort of a view query that includes where stories ID equals question mark. And the question mark here is a sort of signifier of a parameter that can be filled in whenever that view is executed. And now the the view does have the necessary information in order to figure out what state is missing and what state is not. So if the application, for example, is curious about story 7, it'll execute this view query for story ID 7. So essentially substituting the question mark parameter for the value 7. And crucially, what partial state enables is that these queries can miss. So for example, again, if the application here tries to execute a query for stories with the values story 7, the read that ends up in the system might find missing state, indicated here by a hollow green box. And in that case, what the system internally is going to do is issue an upquery for state 7. And it's going to do that to the immediate ancestor of the view that we missed in. So in this case, this upquery sort of, you can think of it as a request for a summary of all relevant past deltas to be retransmitted through the data flow. In some sense, you can think of it as the view saying to the join, tell me about 7 again, because I've forgotten all about it. And the join, when it receives this upquery, its role is to send the relevant state back, any state it has for 7. But the join doesn't actually have any state. The join is sort of a stateless operator. And so the upqueries can then recurse. In this case, the join might choose to forward the upquery, say, to the aggregation on the right. And that upquery, again, is sort of, can you tell me about 7 so that I can tell downstream about 7? Now, we need a little aside here because so far we've only talked about state in tables and in views. But there's other state in the data flows too. So recall that the count operator needs to be able to get one new vote and realize that that has to turn into sort of a replacement of the value 42 to 43 because the vote count changed. But in order to do that, it needs to remember that the current count is 42. And so the way it does this is the count operator actually causes an additional materialized view to be installed internally in the data flow. It ends up materializing its own output and then using that to process later deltas. And that internal state can also be used to satisfy any upqueries that occur. So here, when the upquery comes from the join, it might be that the aggregation is able to find the relevant state, the state for story 7, in its internal materialized view. And then it can respond with that state, saying the current state for 7 is that 7 has 43 votes. And it's going to send that as a normal delta through the regular data flow. And this is a key point. There's no need for any special operators or like different forward and backwards query processing. The response is just a single message along the normal data flow that holds the sort of current state of the source for the requested key. When that response arrives at the join goes, oh great, I can now try to respond to the upquery I got for 7. And it has to do its normal data flow processing. And so it's going to do lookups into stories to produce the final deltas in response to its upquery and send that down to the materialized view. When that finally arrives, the materialized view applies it to its materialized view in order to fill the hollow green box, to fill the missing state. And at that point, we have the information that we need in order to respond to the client that ultimately asked us, hey, what's the result for this view for story 7? And what's really nice about this is that the state has now been populated, right? There's no longer a hollow green box. And so if another application comes along and issues the same view executed over the same parameter value, story 7, we can just respond immediately, right? Because that state is immediately present. And this brings us to the cool part that we want to enable with partial state, which is the ability to evict state over time. Imagine that, say, a year goes by and no one really cares about story 7 anymore. Well, the system is now allowed to evict story 7 from any materialized views it keeps. So it can just send a message to the through the internal data flow to say, evict any state you have for story ID 7. And this might evict the state both from the aggregation and the materialized view, or only a subset of those. And this means that we've now saved memory that can be used to materialize other results that are popular and are still being accessed. And I mentioned also that not being able to evict also means that we're wasting compute. Well, this model actually allows us to not waste that compute after all. If we get, like imagine some change comes along to story 7, like someone changes the title or something like that, that's going to cause a delta to arrive into the data flow starting at the stories table and flow along the edges. Well, when that story 7 arrives at the join and the join does a lookup into the aggregation state and it finds that that state is missing because it's been evicted, it turns out that now the join can just discard that update. It doesn't need to do any more processing. And in fact, it can't because that state is missing anyway. But the fact that it's missing in the aggregation means, and the thesis goes into some detail about this, that that state must be absent downstream as well. And so by discarding the update, we're not wasting compute. We're also not leaving any downstream state stale. Now that we've talked through the sort of whole thesis title, I think it's time we take a little bit of an intermission and talk about related work, because there is a lot of related work in this space, and now you have the necessary context for us to talk about it. So the first is materialized view maintenance. So I've talked a bunch about materialized views and how they've existed for a while, and materialized view maintenance is an area that has seen a lot of work. But generally, that work tends to target a different workload than what we're going for here. The workload that's intended tends to be things like, there's like an analyst that comes in and checks some important results of some big complex query only occasionally, and it would be too slow to execute that query like those few times that the analyst comes in. But generally, there's sort of a high frequency and high volume writes, but the reads are infrequent, even though they do have to be fast. And this means that the workload has sort of been tailored towards being able to make maintenance really efficient and not really focus so much on the performance of reads. This also means that these systems tend to have little or no support for on-demand queries. The queries are often compiled into the program in some way, for example. And they also have no or little support for eviction because it's not really needed. The query is executed in full by the analyst, and if the analyst doesn't care anymore, they just remove that entire view. The other thing that comes up a lot in trying to solve this problem is these automated caching systems. And we've seen a decent number of these both out of industry and out of academia. Unfortunately, few of these, especially the ones from industry, are general purpose. They're usually tailored to a particular workload that that company and its engineers had in mind. They're not really built for you to just plug and play with your own application. Many of them also don't really support invalidation. They don't have incremental updates. Sorry, they only support invalidation. They don't really have incremental updates. And this, of course, means that you end up wasting a bunch of compute by having to recompute the query every time. These systems are also often limited to specific ways of interacting with the database and not the general purpose just SQL views like we're thinking about here. They might require that you go through some application framework or some ORM, whereas we're targeting here caching for arbitrary SQL queries. And the third sort of large sphere of related work is data flow and other stream processing systems. And as I mentioned, there are many definitions for this, but in general, these are usually focused on write performance and not read performance. The intention here is that you have some data pipeline and you're just going to like shove writes through there and they go into all these systems and have to be computed. And again, there's sort of an expectation that you have queries you care about, but you only care about them infrequently. And in general, these systems tend to focus on strong consistency, which usually comes at the cost of read latency. The read normally has to flow through the write pipeline in order to give consistent results. And this obviously means that the results are much slower to generate than what Noria can do with its eventual consistency. Similarly, there isn't really support in these systems for on-demand compute and eviction. Rather, it has a similar flavor to materialized view where you sort of set up the query and then it's just going to materialize all the results and maybe you can query over them. If you want to evict from a view, you terminate the process and start it over or something like that. And that is, of course, very unfortunate. So now that we've talked through this a bit, you might think, well, are we done? We have, after all, now sort of sketched out partial state and it seems to work, so great. Well, if we were done, this thesis wouldn't be very valuable. And so no, we're not done. It turns out that this problem is kind of hard in practice, even though the model is fairly straightforward. In particular, we have to ensure that the data changes only take effect exactly once. It would be bad if an insert, like if you did an insert to a table and it just never happened. It was never applied. That row never appeared in views. It would also be a problem if that insert somehow got duplicated and you ended up with that same row you inserted suddenly appearing multiple times in different views. Now, traditionally, this is easy. If you think of something like a relational database, all you really have to do is just look in the tables and the indices and scan the tables if necessary, but you're only going to encounter each row once. And if you don't, then it's a bug, and that's really about it. For us in this model, it's a little bit harder because there's a lot more concurrency in the system. In particular, upqueries hold past state, right? They're summaries of past state, which means that they sort of repeat state that is already sent potentially elsewhere in the graph. Imagine, for example, that someone does an upquery for story 7 at the same time as some other application path is updating story 7. So now we have two messages in the system that both talk about story 7, and we need to make sure that we don't end up mixing these up and produce incorrect results. Similarly, I mentioned how updates that flow through the data flow graph, if they encounter missing state, they might end up getting discarded because we don't want to waste compute maintaining something that no one cares about. But there can be cases where this goes wrong too, where there might be downstream state that does depend on that update, but the update encounters missing state and so we throw it away. And now that downstream state is just permanently out of date, which would not be good. So there are a lot of potential hazards here, and unfortunately, I don't have the time to go through all of them. For that, you would have to read my thesis. But we're going to focus on one that I think is particularly interesting. Specifically, we're going to look at incongruent join evictions. And if you don't know what these are, it's not that weird because it's a term that I made up. But hopefully, over the course of this, you will understand what it means and why it's a problem. So let's, given that I made it up, start by understanding what is an incongruent join. So here I'm showing you a query and a data flow again, but the data flow and the query are both different from the ones I showed you earlier, even though they look somewhat similar. In particular here, we have the two tables stories and user, and the query is just a straightforward join between the two. The idea is that every story has an author, but in the stories table, that's just stored as the author ID, the author's user ID specifically. And then the user's table is the one that has information about the user, such as their name. Now, when we want to query and display a story, we probably care about the user's name as well. And so we really want to join these two tables on the author ID. So the output, the thing that we get from the materialized view, contains the author name as well. And what makes this an incongruent join is that the query key is not the same as the join key. The query key for the materialized view is the story ID. The join key is the author ID, which is a different column. And now this isn't a problem in and of itself. So let's just walk through how this works for an upquery and see that upqueries tend to work pretty well in this case. So imagine some application comes along and asks for story 7, an upquery goes to the join is stateless, so it forwards the upquery, in this case, to the stories table. The stories table then responds with, yep, for story 7, the author is user number 42. And then the join does a lookup when it receives that response, does a lookup into users, and looks for, give me the information for author number 42. And let's imagine that it returns 42, author name or username, Lena. And then the join receives the response to the lookup and produces the state for the downstream materialized view that holds 7, the other columns for stories, and the author name being Lena. That gets populated in the materialized view, and subsequent reads get the right result. So far, so good. But now recall this figure from a little while back, that if we have a dataflow update that goes through the graph and then encounters missing state, then we just throw it away. This causes us some issues when we're looking at incongruent joins. So imagine that the author changes for story 7. So this will be represented as a negative for story 7 and author user ID 42, and a positive for story 7 with author 43. And let's look at what happens when this moves through the data flow. Well, these deltas arrive at the join, and the join has to change the deltas so that they fit the downstream materialized view, which means that, again, it needs to do lookups into users. It starts by doing a lookup for 42, and again finds that the name for author 42 is Lena. So it fills that into the delta. And then it moves on to the positive, which says that the author here is 43. So it does a lookup for 43, but now imagine that that lookup misses. And as a quick aside here, you might wonder, well, how could this happen if users is a table? There are a couple of answers to that. You could imagine that that table is maybe not in memory, or that particular row is not in memory and would need to be fetched from disk. Noria doesn't support this, but you could imagine that being the case. More realistically, and in the real system, what I'm giving you here is a simplified version of the system and a simplified query, but you could totally imagine that users here was not a table, but actually a view in and of itself. And so it has some large data flow above it that's maintaining it. And then you could easily imagine that some entry in that view is missing. Well, this leads us in a bit of a problematic case, because now we don't really know what to do. We can't produce the needed update, right? We don't know the author name for user 43, so we can't produce the positive that's needed in order to fill in the new result for story 7 in the downstream view. We can't forward just the negative, because if we did, any subsequent read for 7 would just get an empty result, which is clearly not the case. There is a story 7, we just don't know its author name. And we also can't drop the update altogether. If we did, the downstream view would continue to believe that the author was 42, Lena, and it would never see the update that we applied to stories. Essentially, we're violating the earlier mentioned exactly once rule. And you might say, well, John, don't be silly. We can just fill the result. Like, okay, 43 is missing. Just do an upquery for 43 or something, fill in that state, and then when it comes back, finish doing what you were doing. And that's an attractive idea, but unfortunately, it doesn't work so well in practice. The reason for this is that while we're waiting for that value to be filled, we would have to hold up the data flow. The join can't process any more updates, because those updates might depend on the update that we're currently in the middle of processing. They might change the author from 43 to 44 or something like that. And not only that, but it turns out that in really bad cases, not only are we holding up the data flow, which means we can't process any more writes through this part of the graph, but we can even end up with deadlocks. I'm not going to go through an example of how that can happen because it's a little involved, but you can end up with a case where the join can't process the update until the upquery finishes, but the upquery cannot finish until the join finishes processing its current update, which obviously would be bad. So that's not really a tenable option. So what do we do instead? Well, partial state actually gives us the solution that we need. It gives us the mechanism that we need, and that is evictions. It's true that we don't know what the author name for author 43 is, but we can just tell downstream that. We can send an eviction downstream for story 7, so that now story 7 in the downstream view is marked as missing. And the system can actually detect incongruent joins and only send the eviction when this is actually the case. And the reason this works is because now any later query for story 7 is going to find missing state and then go through the normal upquery process, which we already showed gave the right result. So now that I've given you some idea of some of the mechanisms that are needed in order to get partial state to work, let's look at whether partial state as a whole and its implementation in Noria actually works. Is it actually useful? In order to answer this question, we need some kind of realistic test subject. In my case, I chose to look at Lobsters, which is a Hacker News-like news aggregator. In particular, you have users who submit stories. Those users can then vote for and comment on those stories, look at top lists of stories by their popularity, and that kind of stuff. The reason I chose Lobsters specifically is because Lobsters is open source, and so we can actually see what queries it issues when different pages are loaded. Furthermore, there are data statistics available for Lobsters, so we know things like which pages are accessed with which frequency, the distribution of votes and comments to different stories, which means ultimately that I was able to create a workload generator that can synthesize Lobsters-like requests. And the reason we want a workload generator like this is so that we can increase and decrease the supplied request load for the system and see whether the system keeps up as we keep ramping up how many requests it has to serve. Also, the generator produces just page requests, and then I have written different adapters for different backends like MySQL and Noria that then issue the same SQL queries as the original Lobsters application did with the same distributions. And this means that we don't have to go through Ruby on Rails, which Lobsters is written in, and we avoid measuring overheads from there. So let's look at the throughput that this workload generator achieves with a couple of different configurations. So first, this is the performance, the number of pages per second that MySQL can satisfy. And here I'm running MySQL on a 16-core Amazon EC2 instance, and this is just like the workload generator is generating all the different page requests, and when you push it beyond about 400 pages per second, MySQL ends up saturating all the cores on the machine and is not able to keep up with any higher load. It's worth keeping in mind here that this is with a denormalized schema. The Lobsters authors have already done some work to optimize their queries. In particular, there's sort of a query in there that looks a little bit like the story and vote join and aggregation we looked at before. And there, they don't actually do a count in their SQL query precisely because it would be too slow. Instead, they have a count column in the stories table, which means that they can just read. They don't have to do a join or an aggregation. They just get that result in. But every path in the application that changes the sort of score of a story needs to remember to update that field. If you don't include this kind of manual optimization, Lobsters against MySQL can't even keep up with a single page request per second. Now we're going to try to run the same workload against Noria, but without partial state. So this is already a lot better, about an order of magnitude faster, and shows you sort of the power of materialized views and caching. Of course, here we're doing a lot better because the reads don't have to do any work. They just immediately get the response, and almost every read turns into more or less just a key value lookup. But here we hit a different bottleneck. When we get to this amount of pages per second, it's not that we run out of cores, it's that we run out of memory. This machine has 128 gigabytes of memory, and at 4,500 pages per second, we just run out of memory. Trying to run with a higher load, the machine just hangs because it can't allocate any more memory for Noria's materialized views. And this is already with a slight optimization where it only materializes the requested values, because otherwise it would fall over entirely. So it won't, if the application just never asks for story 1, it won't actually materialize that view at all. So let's now look at what happens if we enable partial state in Noria. It suddenly does significantly better. It's about 67% higher than without partial, and about 18 times the throughput that MySQL can achieve. And here, we don't run out of memory. We don't even saturate all the cores. In fact, where Noria falls over here is due to upquery processing, because the upquery processing, the way it's built requires that certain parts of the data flow is only processed by a single core. And so we end up essentially with a bottleneck on a particular update path through the data flow that gets very, very hot when you run at this kind of load. We can see this reflected in memory use too. So here I'm showing the memory use in gigabytes for Noria without partial and Noria with partial near the capacity of Noria without partial. So at around 4,000 pages per second. And you see that Noria with partial only uses about 1/3 of the memory. Now you might ask, well, forget MySQL, like no one does that for real. If I implemented a caching system myself, will Noria really keep up? Can it really sort of replace some existing caching system that I built? And this is a very hard question to answer because it depends on the implementation, the application, the workload. And so instead, what I decided to do was to construct an experiment that sort of tests an idealized caching setup. There are no evictions, no misses. Almost everything is reads, everything is a single key lookup. And then run it against Redis, which is one of the popular key value stores that are often being used for caching. And what you see here is, again, throughput on the y-axis. And this is running just the vote query that we looked at before. So the join of stories with the vote count, and just issuing as many queries of that as we can over time. And again, here against Redis, there are no cache invalidations, and every read is a single key value lookup. Now, Redis is single threaded, which means that it's only using one of the 16 cores. So here's that same number times 16. So this is just assuming that there was like a perfect scalability for Redis, and it could just use all your cores. So this gets to 14 million requests per second. Again, idealized. Now let's see what happens if we try to take that same query, the same workload, and run it directly against Noria. Noria measures up quite well. Remember that the figure on the right here, the bar on the right, is a theoretical maximum for doing single key value lookups against Redis. Whereas with Noria, you get full SQL queries, you get automatic cache updates. It just deals with everything for you, and its performance is still within a factor of 2. Now, we've talked a lot about Noria so far, and I think it's about time we start to wrap things up. So first, I want to talk a little bit about future work. Noria is neither perfect nor complete, and neither is partial for that matter, but these two can probably help each other. In particular, there are a number of things in Noria that are missing, like range queries and cursors and timed window operators, where partial state might be a really interesting part of the solution. Other things that would be nice to have in Noria is things like being able to integrate with some upstream database so that instead of Noria storing your data, you have MySQL or Postgres or whatever you're currently running store that data for you. Because Noria propagates these deltas internally, it could also be used to feed downstream views all the way down to the client to like a mobile device. So the idea is that if the mobile device shows some list currently and some data changes that affects that list, maybe the delta could be pushed out of the data flow all the way to the client. Noria also doesn't have a great story for fault tolerance, but partial state might be able to help here by marking things as partial and as missing when a relevant node fails. Now, before I end, there are a couple of people I want to acknowledge who have helped this work be a reality. The first of this is my committee, Robert, Franz, Sam, and Malta, who have just continuously been working to make this better. Robert and Franz in particular have just continuously been asking me for what the story is, what the purpose is for Noria and for partial. And I think that has made the work a lot better to try to be able to articulate that. Malta as well was a postdoc in my lab for many of the years where Noria was being developed and was a key person in getting Noria to what it is today. Without him, Noria wouldn't have SQL or query optimizations and would really just be a data flow system. And Sam as well is an invaluable resource as a database person who has more sort of database chops than any of us systems people. I also want to thank the MIT Parallel and Distributed Operating Systems group, my group at MIT, who have just been an endless source of curiosity and insight and support over my 6 years of the PhD. And I think they've made me the researcher that I am today. I'd also like to thank my family, my parents and step-parents who have always encouraged me to pursue my interests no matter how geeky they might be. They've sort of been nudging me along to just do what I found interesting. And I think that without that, I wouldn't be here today. And I really want to thank my girlfriend, Talia. I'm amazed that she's tolerated me just sort of locking myself in my room and working on this for as long as I have. I'm so grateful and happy that I have her. So to conclude, my thesis enables materialized views to be used as caches. It does so by allowing state to be missing from materializations and using upqueries to populate such missing state on demand. The resulting system provides automated caching for SQL queries and reduces the need for complex ad hoc caching logic. Thank you everyone for listening, and please ask any questions you might have. Thank you. Nice. Ooh. All right, people. Now, questions, please. I'm happy to answer as many as I can. Of course, tomorrow, what will happen is after I finish this talk, there'll be questions from the audience then too, and then I'll be grilled by professors on my committee for a while. But hopefully that was possible to follow. Hopefully it was understandable, and hopefully you got some idea of what the work is and why. Oh. Tangentially related, has Noria seen corporate interest? Yeah, there's been a lot of interest, but there's nothing commercial at the moment. Can Noria scale horizontally? Yeah, so Noria is distributed. You can shard the data flow and you can put different operators on different physical nodes. And so you can distribute the workload that way. Really like that you changed the graphs. Okay, I'm glad. That was a last minute change. Did Rust actually help you with this, or did it slow you down? I think Rust helped because there's a lot of internal concurrency in Noria to give it the performance it has. And I think debugging some of the weird concurrency things that I've run into without the Rust type system would have been a pain. What does it mean to scale horizontally? It's essentially that you can get higher performance by adding more machines as opposed to buying more powerful machines. Any comparisons between Noria and a Lambda architecture where the queries are shot to the source of truth tables and the update streams and finally merging the results? I don't know of the Lambda architecture well enough. It sounds somewhat similar. Usually the limitations of many of the existing systems that look sort of like this is that they don't have eviction, and that is really unfortunate, as I mentioned in the early work. How much work would it be to add transaction support? It really depends on what you mean by transactions. Stronger consistency is probably not too hard to add. What you really need is some way to propagate timestamps. Adding full transactions would probably be harder because usually what you end up with is you need so much synchronization that the reads have to wait for the writes. And at that point, it's very hard to serve reads without serving them at the speed of writes. Is there any way to attend the live presentation of the talk? Well, I mean, this is the live presentation of the talk, so you are currently attending it. The sort of formal MIT presentation tomorrow is sadly not open to the public because Zoom bombing is a thing, and it's unfortunate. Will you be recording tomorrow? I would like to hear the questions. Yeah, my plan is to record tomorrow as well. I don't know how the recording is going to turn out because it's going to be a Zoom recording. My plan is basically to take the recording from today and the recording for tomorrow, and then look at which turned out better and then post that one. Do you plan to continue your work on Noria? I need a break for a while. Just because, and it's not for a lack of belief in the system or anything like that. It's just, it's been occupying my brain for 5.5 years now, and I just need to think about other things. Are there any alternatives developed at the moment that are similar to Noria or focus on a similar problem? Well, so there's materialized is one example, but materialized is more in the category of the sort of traditional materialized view systems, at least the way I understand the system, where it's more focused on you have this data pipeline and you want to keep materialized views over it because there are queries you need to be able to execute. But those queries are not executed super frequently. Like in Noria, we're imagining the reads happen like an order of magnitude more frequently than writes. And that's not really the workload that materialized is targeting, I don't think. What is the future of Noria now that you're taking a break? I don't know. My hope is that it ends up being a thing that people can use. And I'm talking to some people in that direction, but nothing as of yet. Will your work at Amazon be database related as well? No, my work at Amazon will be Rust related, but will not be database related. Spill the tea. What are you doing at Amazon? I don't think it's a secret. I'm basically going to be working on like building out Rust at Amazon and being sort of a contact person to the ecosystem, and more or less just try to make Rust be a sort of viable option at the scale that Amazon operates at. Have you checked Foundation DB? Could it be a storage engine for Noria? In theory, anything could be a storage engine for Noria. Noria's sort of backend storage is sort of plug and play, although there are some challenges with partial to make sure that you don't get race conditions between the underlying base tables and the reads from the data flow. Like Ryan at Microsoft, in a sense, yeah. I mean, I don't know Ryan's formal role, but probably something a little similar. Will you work on Risotto? I will probably end up having some fingers in that pie, but in some sense, I won't really be working on particular projects as much as I'll be working on infrastructure. Noria is open source, right? Are serious pull requests welcome? They are. Noria is, I would say, currently not production ready. I wouldn't run it for anything where you, like, if you lose data, you lose like millions of dollars. But if you find things that are good improvements, then absolutely. In the data flow graph shown on many slides, there's a single aggregation node, but there's a count plus group by. Are these two operators merged in Noria, or is it a simplification for the presentation? A count plus group by is an aggregation. You can think of it as aggregations need to have something to group by, and they might group by nothing, in which case they're aggregating all of the input rows into a single row, or they might group by a particular column, in which case they aggregate all the rows with each value for that column. Regardless, it is still just one operator. The group by itself is not an operator, at least not in Noria. Could Noria query from multiple backends, such as in a distributed system? Yeah, in theory, you could have different tables in Noria be backed by different storage systems. I don't know that you could have one table be represented by multiple systems. That would be harder. But keep in mind that Noria only really cares about storage at the top of the data flow, like where the tables are. The rest of the data flow doesn't really matter. Let me actually switch to there so you can see my face. What part of the work to be done in Noria do you consider worth for a master's thesis? That's harder. I think there's a lot of work in Noria that could be good for a master's thesis. but it's hard to describe sort of on the fly now. But some of the work that I mentioned already, things like range queries, improved fault tolerance, something like read your own rights, consistency, cursors, better support for like ordered collections. I go through some of these in the thesis itself as well, which I'll post after the defense. How does a PhD defense work? As far as I understood it, your committee will grill you on your thesis and also perhaps on your publications you had to write to qualify for submitting your PhD. So there are many parts to that question. MIT does not require publications to qualify for submitting a PhD. It's just whenever your committee is willing to say that he can do his defense, that's what's required. As for how the PhD defense itself works, I mean, I haven't been through it yet, so I don't know. My understanding is basically they read the thesis and they might have a bunch of questions about the work, about how it's feasible or any gaps they might see in the argument it makes. Usually, I think they then they sort of give a yay or nay decision on, is this good enough to graduate? And then they usually follow it up with edits that they want you to make before actually finishing the thesis and handing it in as sort of an official document. Will your thesis be public? Yes, I will post my thesis. What was the hardest thing to implement in Noria? It depends on what you mean by thing, like what the unit is. I think the hardest thing was probably to get to make reads as fast as they are. So in Noria, the reads are extremely concurrent with very little synchronization with each other, with like the executor, with the data flow, and that was a bunch of work. Kind of surprised that this work was done in PDOS and not the DB group. Yeah, it's a little weird. In fact, before I started this work, the last thing I told my professor was I don't want to build a database, and then look at me now. I think my pitch here is that Noria is not a database. It just pretends to be one. Like Noria is a data flow system, and it just happens to implement something that looks like a database. What was something that was surprisingly easy to implement? So in some sense, the hardest and the easiest things were SQL operators. Like there were some operators that were just extremely simple and I hadn't expected it to be that easy. And then there's some that are just extremely complicated and really annoying to implement. Like multi-way joins are a bit of a pain. Aggregations are surprisingly easy, except when they're not. Right? Like I think before I started this work, I didn't realize just how different a max aggregation is to like a sum aggregation. They're very, very different. So if you miss the materialized view, you do the flow lookup, right? How do you tackle the problem when the flow fails? I don't know what you mean by the flow fails. What do you do to prepare for MIT's PhD? I don't think you really prepare. I think you just do a bunch of research, find things that you enjoy doing, and make sure that you actually want to do research, because you'll be doing a lot of it. Like certainly at MIT, the PhD program is mostly research. You do relatively few classes, so make sure you actually enjoy doing research and being a student. In Noria, are multi-joins implemented as one aggregation or a sequence of aggregates? What were the trade-offs? Well, joins aren't aggregations, but multi-way joins are implemented as chained two-way joins for now. There's nothing fundamental that requires them to be there that way, but think of it more as Noria wasn't trying to innovate in the space of like query optimization or query efficiency. And so I sort of implemented whatever was most straightforward as opposed to like implementing a smart query optimizer, because like the thesis is about partial state, right? So those things are just not important for the purposes of the research. How'd you end up using Rust for Noria, especially considering Rust was pretty beta 6 years ago? Well, so I started this project, I think shortly after the Rust 1.0. And I'd been looking at Rust for a little while, mostly just because I really enjoy doing like concurrent programming and multi-core synchronization and that kind of stuff. And Rust just seems like a really interesting new take on that. I'd been doing a lot of Go work before then, and I was looking for sort of a more elaborate type system, for example. I was really excited by, and so I really just wanted to try Rust for something kind of real. And then I started building Noria in Rust, and I just really enjoyed it, so I continued. So it was sort of the ball just started rolling on its own. Did you consider staying in academia? I considered it. I think I care too much about building things that are useful for many people, like right now, which I think some computer science research focuses on that. But in general, the focus in academia is less on building things just for the sake of being useful. So for example, I like writing documentation, and you get no reward for writing documentation in research land in general. Or like making things like production ready and stable and able to be run by many people is exciting to me, but it's not important in a research prototype, for example. Will you be able to continue making your Rust videos when working at Amazon? Yes. This is, I would not have accepted a position if I could not keep doing them. If you get a thundering herd for a miss, would it issue multiple upqueries until it hits the view? No, actually. The upqueries, so the way that actually works is that the upqueries get deduplicated at the view. So only one upquery ends up propagating through the data flow. The client, the sort of read requests get essentially get batched into a single upquery, which was also a bunch of work to get to work right. While developing Noria, did you experience any things you just couldn't cleanly express in Rust? I don't know if cleanly express in Rust is the right thing here. There are certainly some nightly features that I basically need. I think the one that comes up the most often is Noria is a very dynamic system. Like you can sort of add, remove queries, add runtime dynamically. And this means that internally it does a lot of indirection through enums. Like the data flow is a graph, right? And the node type of the graph is an enum over all the different SQL operators. And sometimes it's really annoying that the variants of an enum are not their own type, because it means that even if I have code that like earlier matched and made sure that this was a join operator, I then sometimes have to like do that match multiple times, even though I know that at this point in the code, it must already be a join. And rather than that being enforced by the type system, it has to be enforced through the runtime, which is annoying. Did you find bugs in the Rust language during the development? I came across a couple of compiler errors that were wrong, most of them in nightly features. I found bugs in things like Tokyo, like the executor, and some of them were just performance bugs. I found things that were missing from the standard library. So certainly some of that. I think that I did find one bug related to like networking and DNS caching a while back, but surprisingly few. How did the new features in Rust during this time affect Noria, like async? Moving Noria to async was a huge pain, but it was worth it. We used to have like our own thread pool it was a pain. And moving it to async was a big, long, arduous process, but it was worth it. Anything that Rust does better than Golang, maybe apart from the more expressive type system and borrow checking, and helped with Noria. I think the low-level control matters a lot when you're building a system like this. Like you can get at the low-level bits in Go too, but being able to have control over like memory layout and cache lines and threads turns out to matter in a bunch of different cases. I did not use any linear algebra crates. No, none of that in Noria. All right, it seems like the questions are starting to dry up. Okay, let's do 2 more. Did you need or use unsafe code to easily do optimization? There is a little bit of unsafe code in Noria, but surprisingly little. There's some that I've sort of externalized to libraries like EVMap, but in general, there are a few of them. It's very little. And some to avoid memory copies in particular local cases where it's safe. I've seen your name in some big Rust crates. Were these contributions related to Noria or just for fun? It was a mix. Things I built for Noria, things I built for like for streams, but much of it was motivated by some need in Noria. I'll post the slides when I post my thesis, which will be after. All right. Thank you everyone for tuning in. I hope it was useful and interesting. Again, I will post a recording of this after I do my actual presentation in defense tomorrow. Thank you everyone for coming out. It's been great having you in chat. See you next time. Bye everyone. So long, farewell. Auf Wiedersehen, goodbye.